Everyone, we're going to look at 3.10. There's a little bit of calculation to do with your calculators. This is just about the final topic for Unit 3. So our goal is to determine the relationship between orbital radius, orbital period, orbital speed, and mass. And when I say that, I'm referring to of a satellite or of a planet going around another planet, or a planet going around a star, or a moon going around a planet. So a satellite in geosynchronous orbit takes exactly 1 day to orbit the Earth. By doing so, it's always above the exact same point of the Earth's surface. Now, just think about why that could be desirable. Think about the satellites we use every day, and how our cell phones or televisions or whatever are contacting them constantly. Think about why it would help to have that satellite always above the same point on the Earth at all times. So when we do that, those satellites are said to be in geosynchronous orbit. So in the space below, solve for the period t of an object in geosynchronous orbit. So I just want to solve for basically how many seconds are in a day. So let's start with, we'll do this in blue. No, I'll do it in black. T equals, well, we have 365 days in a year, about. And we have 24 hours in a day. We have 60 minutes in 1 hour. And we have 60 seconds in 1 minute. Minutes cancel, hours cancel, days cancel. So if we multiply out, we should get how many seconds are in a year. So we get the period is 3.154 times 10 to the 7th seconds. So that's how many seconds are in. Oops, I made a mistake there. I did seconds in a year because I did that with my other class. I want seconds in a day. Let's fix that real quick. So that'll just be 1 day. Okay, so it's actually a little bit easier. So let's do 24 times 60 times 60. Okay, that makes more sense. 86,400 seconds. Okay, so the satellite is moving counterclockwise as viewed from above. Sketch and label the velocity vector, the force, and the force of gravity acting on the satellite. So counterclockwise would be this way, the opposite of the way a satellite goes. The velocity we'll do it in orange. That's going to point tangent to the circle in a straight line. The force of gravity will point to the middle of the circle. So it says carefully sketch 3 R values on the image. Excuse me. R for the radius of the satellite's orbit, RE for the radius of the Earth, and RA for the altitude of the satellite above the Earth's surface. So let's sketch these all out. We'll do these in blue. So RA is the distance from the Earth's surface to the satellite. RE is going to be the radius of the Earth. And R is the radius of the satellite's orbit. Notice that R is simply the radius of the Earth plus the altitude of the satellite. So R is equal to RE plus RA. That's important to include the radius of the Earth and the altitude of the satellite above the Earth's surface when finding R. If we are at Earth's surface, there is no altitude. The altitude is 0. That's why the radius would just be the radius of the Earth. So starting with centripetal force equals MAC, solve for the velocity of the satellite in terms of R, M, and physical constants as necessary. Think about what force is the agent of the centripetal force. So before we get into this, I just want to talk about why does it have to be moving? Why can't it be stationary? Why does it need to be moving? So I'm just going to go on a little bit of an aside here. You could write this down wherever, but it's mostly just for you to think about. So let's say I have a flat surface and I have a tower and I have a cannonball firing out of that tower. And this is on Earth. If I fire that cannonball, what trajectory is it going to take? It's going to do something like this. Now I'm going to repeat this. But now I'm going to have a really big cannonball. So let's say now the curvature of the Earth is not negligible. Well, actually, we'll get to that soon. So let's say I fire the cannonball a little bit faster. It's going to do something like this. And if I fire it even faster, it's going to go even farther. Eventually, the Earth's curvature is no longer negligible. It's going so far horizontally that the Earth's curvature is no longer negligible. So now if I just kind of draw an Earth, a mini Earth here, we'll do it in blue. That's a bad circle. Let's try another one. All right, could be better. Okay. So if I have a really tall cannon now, a really tall tower with a cannon on top, and I fire a ball, it's going to fire and it's going to eventually hit the ground. If I fire it a little faster, it's going to go farther before hitting the ground. But if I fire it with the right velocity, as it falls, its trajectory will match the curvature of the Earth. That's what orbit is. It is a state of free fall. Okay. When we talk about people on the International Space Station, okay, so now picture instead of being like a cannon fired around, let's say you're on the International Space Station. We saw last class that the acceleration due to gravity on the International Space Station is going to be 8.6 meters per second squared, about. So why don't those astronauts just fall to the bottom of the ship? Well, they are falling, but the spaceship or the space station is moving so fast horizontally that as they fall, its trajectory matches their path. So they are falling with the space station. The space station is falling around the Earth. So as they fall, it's just going so fast horizontally that it keeps missing the Earth. Okay, so people on the International Space Station are in a state of perpetual free fall. So that's why we need to be moving. If the International Space Station or this satellite stopped moving, the force of gravity would just pull it down to the Earth and it would hit the Earth. But by moving, as it falls, you can kind of see that path here. As it falls away from that straight line, it keeps missing the Earth because the Earth is curving as well. So that's why things in orbit have to be moving. If they don't move, they'll just fall to Earth. So by moving tangent to their orbit, tangent to the path of their orbit, they keep missing the Earth as they fall, or we keep missing the planet as they fall. That's how all orbits work. So let's start with the equation, the sum of the forces centripetal equal MAC. So FC is going to be all the forces that keep this thing in a circle, all the forces that point in and out of the circle. In this case, it's just the force of gravity. So FG equals MAC. But we want to solve for V. Where can we get V into this formula, and where can we get M and R into this formula? Well, the force of gravity equation is just G times the mass of the Earth times the mass of the satellite all over the distance between their centers squared equals the mass of the satellite. And this is going to be V squared over the radius of the circle. So the radius of the circle, the radius of the satellite's orbit, is the same as the distance from the center of the satellite to the center of the Earth. So those R's are the same. So we get a little bit of canceling there. When we're talking about MAC, we're talking about the object that's moving in a circle. That's the satellite. So this mass cancels with this mass here. What we're left with is this equation. V squared equals G, mass of the Earth, over the radius of the satellite's orbit. So V is equal to the square root of G ME over R. Note that I can write this another way as well. We defined RE and RA. So V you could also say is equal to GME over RA plus RE. So what factors don't affect, or do and do not affect the orbital speed of the satellite? Well, big G, but we're not going to talk about that. The mass of the Earth, or the mass of whatever you are orbiting, the radius of the radius of your orbit. So if the mass is bigger, you have to be going faster. That makes sense because if the mass is bigger, it's pulling you with more force, right? The force of gravity equation tells us that if mass is bigger, there's more force. So if it's pulling you with more force, you're going to move faster to avoid hitting the object, to avoid hitting the planet. If R is bigger, V is smaller. So you don't have to be going quite as fast if you're farther away. Because if you think about it, if you're farther away, the force of gravity is smaller. Therefore, you don't have to be going as fast to keep missing the Earth. The other thing that doesn't matter here, at least with this satellite example, is whether or not RA or RE is bigger here. All that matters is their total together, the total R value. So if the planet had a bigger radius, but the altitude was smaller, that would be the same as if the altitude were bigger and the planet had a smaller radius, as long as those two add up to the same number. Notice here that the mass of the satellite does not matter. Now that goes for any objects orbiting each other. For the Earth going around the sun, the mass of the Earth does not matter. For the moon going around the Earth, the mass of the moon doesn't matter. So the object that's doing the orbiting, that object's mass does not matter. For the object that's being orbited, that one's mass does in fact matter. And again, the important thing is R is their center to center distance. So using your equation for number 4, create an expression for T, the orbital period, in terms of R, M, and physical constants as necessary. So what I'm going to do is I will start with this V equation. Remember, for an object going in a circle, I can replace V with 2 pi R over T, where R is the radius of the circle, the radius of its orbit, and T is the time to go around once. So plugging that into the equation up there, I have 2 pi R over T equals the square root of G ME over, I'm just going to leave it as M, just clean it up a little bit, but we know it's the Earth, over R. So I'm going to get T alone, so I'm going to square both sides. So I get 4 pi squared, R squared, T squared equals GM over R. Now I'm going to do some cross multiplying to isolate T. So I get 4 pi squared, R cubed over GM equals T squared. So I get 4 pi squared, R cubed over GM. Take the square root, that's equal to T. Now, if you really wanted to, you could take the 4 pi squared out and make it 2 pi out front, but it's not really entirely necessary. So which factors do and do not affect the orbital period of the planet? Very similar to what we saw before. The mass of the satellite does not matter. What matters is the mass of the object that's being orbited and the radius of the satellite's orbit. Now explain why your answers to 4 and 5 support one another. Well, think about this. If you're going faster, the period is going to go down. If you're going slower, the period is going to go up. So notice how here, V and R have some sort of an inverse relationship. Here, T and R have a positive relationship. Here, V and M have a positive relationship. Here, T and M have an inverse relationship. So that kind of makes sense. If the mass were to get bigger, it would have to be going faster, which would reduce the period, because if M gets bigger, the period gets smaller. So what I want you to do right now, and you can do this on your own, is use these values. This is the mass of the Earth, the radius of the Earth, and the value for the gravitational constant. and I want you to solve for the altitude that the satellite must be placed at to be in geosynchronous orbit. So you're going to use this equation here. You know T from the front page. Okay, so T you have. I gave you G, I gave you M. R, be careful. This is the total R. You need to find RA. So after you find the total R value, subtract off the radius of the Earth, and you will have your altitude's radius. So be very careful there. All right, make sure you show your work and circle the final answer. And the other two things I want you to work on are multiple choice B, question 10, multiple choice B, question 13, and this question here. Show your work for all of these. So you're going to submit all this stuff, and we'll go over it when I'm back. I was thinking about doing class 3.L today from the workbook, but I think this should be good for 2 periods because you can keep yourself pretty busy doing this and working on these questions. At this point, you should be able to answer pretty much every AP Classroom question. If you have any questions, shoot me an email, and hopefully I will see you on Wednesday.